All right, what's up, everybody? It's time to talk about matched pairs. This is the last topic that we have to cover. Test is coming Tuesday, so again, use your class today productively. Use your weekend wisely. Come ready for this test. I am not sure if there's going to be a retake. Even if there is, you don't want to have to worry about it. So do what you got to do this weekend. We'll do a little review, answer any questions you might have, send them in Remind or Google Classroom so I can use those to help prep for Monday. Monday, we'll answer questions and practice a little bit. Test on collecting data Tuesday, ACID. And then after Thanksgiving break, we'll start fresh with a new unit. So anyways, let's jump right in here. Let's talk about matched pairs. We're going to learn some hypothesis tests and confidence intervals in the second semester. And one type of test interval we'll look at is a paired t-test interval. So close to the end of our course, sometime in April, we'll come full circle back to this matched pair stuff. I guess halfway circle because we're like not at the beginning of the class, whatever, third of the way circle. Anyways, Celsius is kicking in. Feels real when I got the Celsius. Anyways, matched pairs, let's do it. So here's the general idea. 3 different pictures we're seeing here to help us look at matched pairs. Side note, great strategy if you're confused about something. Like when I get these images, I just go to Google, type in matched pairs experiment, click images, and a lot of visual descriptions come up. So if you're a visual learner like me, that's a great thing to try, right? Type in confounding variable, blocked experiment, click images, see what pops up. So here's the deal. In a matched pairs design, we're looking over here on the left with the dots, right? Let's say we start with these participants, experimental units, whatever. We got some blues, yellows, greens, light blues. So in a matched pairs design, it's what it sounds like. We're going to match up certain pairs for some reason. We'll kind of get into that with different contexts. So what I'm then going to do is I'm going to take my participants and I'm going to pair them up. In this case, I'm going to pair the blue with the blue, the green with the green, yellow with the yellow, light blue, right? Maybe it doesn't make sense to compare blue person to green person, right? Maybe it makes more sense to pair blue and blue. From there, once I've created my matched pairs, quite literally, I am then going to randomly assign treatments. We know in an experiment, we always need random assignment of treatments. So from here, I'm going to randomly assign one of these blue people to get a treatment and one of these to get whatever, other treatment or placebo. Maybe I flip a coin to do that. Maybe I number them 1 and 2 and generate a random number. Whichever number comes up gets the treatment, the other person gets the placebo. Maybe I write both of those people's names, put them on papers in a hat, mix them up, take one, that person gets the treatment, other person gets the placebo, right? However we're going to do it, we're then going to randomly assign treatments. So one of each pair will get a treatment. One of each pair will either get other treatment or placebo, right? And then we can kind of continue with the experiment. So that's the general idea. That's what we're seeing here. On the bottom right, we're seeing the same thing, right? We start with our experimental units. Then we do some screening for some reason. Maybe we want to pair people. I don't know. Maybe these people, 2 people are similar in some way. And again, we'll see some of those kinds of ideas come up in the context later in these slides. And then from there, one of these 2 people gets the treatment A. One of these 2 people gets treatment B. And we make sure we randomly assign. And then just to kind of cap it off up here on the top right, like a really common matched pairs design is before and after data. Maybe I'm looking at like how many AP multiple choice questions could you, or I'm sorry, how many data analysis SAT questions could you answer correctly before taking AP stat and after AP stat? So like maybe this is, I don't know, Bianca, right? And then maybe this is, I don't know, Jaden. It doesn't make any sense to compare Bianca's before number to Jaden's after number, right? That would be silly. So instead, we're going to pair certain values, right? I'm going to pair Bianca's before, Bianca's after. I'm going to compare Jaden's before, Jaden's after. Although, of course, Jaden would not answer fewer questions correctly after AP stats. But so before and after, just a really common scenario where we want to pair 2 specific data values. And we'll see lots of tables like this sloppiness up here, circling in black when we get to those paired t-tests and intervals in the second semester. So that's a general idea. Take our experimental units or subjects. For some reason, we might want to create pairs. If we do, right, pair them all up and then randomly assign treatments within those pairs. So the best way I think for us to dive into this is with an actual question. We had a packet of multiple choice we did in groups the last time I saw you all. I think that was Friday, right? We did the multiple choice. We did free response part A was with this context. Remember the twins, but we skipped A and B. So you have this in that packet. Best case scenario, you're going to take that packet out right now. You're going to pause the video and you're going to kind of follow along as we go. Maybe you even paused it before and took some notes, which I probably should have said. So here we go. Ignore the fact that my hair looks ridiculous. Dermatologist is going to conduct an experiment to investigate the effectiveness of a new drug to treat acne. Dermatologist recruits 36 pairs of identical twins. Each person in the experiment has acne, and each person in the experiment will receive either the new drug or the placebo. After each person in the experiment uses either the new drug or placebo for 2 weeks, dermatologists can evaluate improvement in acne severity for each person on a scale of 0 to 100. Each twin in the experiment has a severity of acne similar to that of the other twin. However, the severity of acne differs from one twin to another. Now, before we jump into this question, side note, part A asked for the treatments, experimental units, and response variable. Many of us got 2 of those things correct. So response variable is that improvement in acne severity for each person on a scale of 0 to 100. So that's our response variable right there. Most of us also had the treatments correct, which are going to be the new drug or placebo, right? So in blue, we're seeing our treatments. But many of us incorrectly answered the experimental units. Many of us wrote 36 pairs of twins. The experimental units are who or what we actually apply treatments to. So what you want to imagine is, who am I applying this new drug to? I'm not giving the new drug to a pair of twins. I'm not giving the placebo to a pair of twins. I'm giving those things to each individual person, right? Some of the people get the new drug, some of the people get the placebo. So each of these individual 72 people is receiving some kind of treatment. So the 36 twins is an incorrect answer for the experimental units because we're not, 36 pairs, because we're not giving each pair just one treatment. Each individual person gets a treatment. So the only correct answer for the experimental units are the 72 individuals that are participating in this experiment. Just like in the 2019 free response, we weren't spraying individual insects with fungus. So the experimental units we couldn't just say insects because we're not spraying insects. In that case, we were spraying the groups or the tanks. So the experimental units, we were applying the fungus to groups of insects or containers of insects. So back to matched pairs. So this box right here is the reason we want to create a paired design, right? It does not make sense for me to compare what happens with my acne to some other twin, some other person's acne. I want to pair me up with my identical twin who has the same initial acne severity, right? Similar to mine. So in this case, we want to pair the twins together. And part B is asking us, for this experiment, what's the statistical advantage of using a matched pairs design? Now, we know a great way to start this is always to reword the question. So a statistical advantage of using a matched pairs design versus completely randomized. So statistical advantage of using matched pairs design where twins are paired. Now, at this point, you need to pause the video and start talking to those classmates. What's an advantage of pairing the twins together, giving one twin the placebo and one twin the new drug, as opposed to, right, the alternative approach would be to just take 36 people get the placebo, 36 people get the new drug, and then we compare in the end. This would be a completely randomized design. Right? That's what's being referenced here. But that would not be as effective as a paired design. And the question is, why? So take a minute, pause, talk to your neighbors. So the reason we want a paired design is because of what's in that yellow box. Is if we use matched pairs, or maybe a better way to say this is, the effectiveness of the new drug might be impacted by the initial severity of the acne, right? Maybe the new drug works better with really severe acne. Maybe the new drug does a better job if the acne is not that bad in the beginning, right? But maybe that initial severity of acne affects the performance of the new drug, right? That seems logical. Just like with Carafon grow, maybe the initial condition of the soil and the land affects the ability of the grass to grow. So here, right, maybe the effectiveness of the new drug is affected by initial severity. So if we pair the identical twins, we can actually, right, we can compare the effectiveness of the new drug to the placebo for people with the same initial level of acne severity. And as a result, can actually determine whether the new drug causes, causes improvement in severity. With a randomized design over here in red, it's possible if we just pick 36 random people, right? Maybe these 36 random people have acne severity that's not super severe. And then maybe these people over here have acne that's really severe. Maybe all of these people see great improvement in their acne severity. But because they all started with really severe acne, maybe they saw the most improvement, not because the new drug works, but instead just because maybe it was easier to clear up. Maybe it was easier to show improvement since you were starting super severe. So here we have a confounding variable. We can't decide. Did these people show the most improvement because the new drug was more effective? Or did these people show the most improvement just because it's easier to show improvement with initially very severe acne, right? We can't decide which of those two things led to the improvement in acne severity. So to eliminate that potential confounding variable, to eliminate that thing that prevents us from actually establishing or determining the effectiveness of this treatment, we use this matched pairs design. Next up, part C, back to random assignment, right? We have to know how to randomly assign treatments, take random samples, SRS, stratified cluster and stuff, right? We got to master this. So now I referenced this in the beginning. We got to decide how can the treatments be randomly assigned using a matched pairs design to which twins are paired. So now we're writing a procedure, all right? So we got a pair of twins. And the question is, how can we decide which twin gets what? And there's a lot of ways we could do that, right? So we could say for the first pair of twins, write each person's name on a piece of paper. Put the papers in a hat, mix them up. And the reason we want to mix them up, right, is that's how we're going to randomize. Choose one paper, or in other words, one name, and that twin receives the new treatment, and the other receives the placebo. And then repeat that process for all 30, or I should say for the other 35 pairs of twins. That's one way to do it, using names in a hat. That's not the only way. Also, you totally should have paused this and tried this on your own, which I forgot to say, but I'm not going to re-record this whole video. Maybe think of another way to do it. Maybe here's an opportunity to pause and try something different. Pause. Celsius break. I really can't wait to get back in class with this. Maybe we try something else. Maybe for each pair of twins, flip a coin. One of them's got to be older, right? If the coin lands on heads, the older twin gets the new treatment. If it's tails, the younger twin gets the new treatment. That works. Or you don't like those methods. I think I like the coin one. That other one works pretty well. Also, sure, we go with the random number thing, right? Just to get a little more review in here. Without me typing it, we could, for a pair of twins, give each twin a number. One's 1, the other's 2. Use a random number generator, generate a number. Whichever number comes up, that twin gets the new treatment, the other twin gets the other. So that's a little bit of matched pair. So to wrap up, we're gonna have some Edpuzzle questions pop up. Now, if you're watching this as a class, it is totally fine for you to answer these as a group. I want you to have those discussions. If you have your own laptop out, right, you're gonna see these questions, the screen's gonna pause. and it's going to ask you to answer each of these. So we've got 4 of these. But again, right, if you're doing this as a group, I might see for period H only 1 person under Edpuzzle. And that's fine, assuming that you're all actually participating. Maybe it's good if you have your own laptop out, whatever, do what works. I'm going to trust you guys. You're going to show me you did the right things when you ace this test, right? Right. So here's the deal. Professor wants to study the effectiveness of a new study tool for a course. There's 150 students registered for the course. Professor ranks the students according to the cumulative average in the prerequisite course. For every 2 students in order from the list, the professor flips a coin to assign 1 student to use the new study tool and the other the previous study tool. See Lincoln creeping around. And so what we want to figure out is which of these experimental designs, because I now realize I deleted the question, do we see? Do we see a completely randomized design? Do we see a randomized block design, which we looked at yesterday in our video? Or do we see matched pairs, which we're seeing today? See what you think. Talk to your neighbors. And if you're stumped, I'm going to eliminate these because those are sampling methods. Talk to your neighbors about why this is matched pairs. Maybe discuss why, or what would you underline up in the question that tells us we're going to pair 2 people together. We want to see if some new study tool works in improving grades. Well, I'm not going to compare the best student in my class to the worst student in my class. That wouldn't necessarily, I shouldn't say worse, but least successful person who hasn't been doing all their homework, because anyone in this class who has a bad grade, that's on you. You have a bad grade because you're choosing not to put in the work. So start doing that stuff. But anyways, right, I want to compare students that are at a comparable starting point and of comparable abilities. If I got a 50 average, it's a lot easier to raise that up than if I have a 99 average, right? So I don't want to compare a 99 to a 50. 99 can only go up a couple points. 50 can go double their grade, right? That's not comparable. So here we're going to want to pair up the people who have similar grades. And that's why we're seeing this. We're listing everyone in order. It tells us it literally tells us right here that we're pairing them, giving 1 person each pair, the old or the new study tool, right? And we're pairing because we're based on ability. Next up, pause it. Let's see what you got. I also apparently, at least I only partially deleted this question. Did not mean to do that. All right. So just ruined everything. Sorry. This will pop up on your screen. Try it out. I'm making the video take unnecessarily long. I apologize. This is a disaster. Here we go. Eventually I will get to this. Bear with me. Sorry. Don't yell at me. Well, why is this the widest text box ever in history? It's my least favorite thing about this software. There we go. Pause it, read it, try it. And hopefully you decided we've got 150 people. And in this case, we're just taking those 150 people. 75 get one treatment, 75 get the other. We're not pairing any 2 particular people together. We did not group people in any way before we randomly assign treatments. This is just our straight up, completely randomized design. How about this one? Read it. I'll pause it. Read it. Answer it. Discuss. This time, we didn't just take the 100 people and split them into treatment or control. That would have been, that would have been completely randomized. We didn't do that. We are not, it doesn't look like pairing any 2 particular individuals together. Instead, what we're doing here is we're first creating groups, male and female. Then we are randomly assigning treatments for the 50 males and randomly assigning treatments for the 50 females. So here we have blocked this experiment. Anytime we create groups based on something we think is related to what we're measuring, maybe we think that being male or female is going to be related to the effectiveness of this pain relief medicine. So we want to compare just males to males, females to females. Back to the video yesterday, when we create these groups, that's when we have our randomized block design. And to close it out, read it, pause it, read it. And let's see what you got. This time, different context. We're looking at Effective volume on driving reaction times. I will tell you right now, I crashed my car 2 weeks after I got my license, and it's because I was too worried about blasting music with all my friends in the car, and then I drove directly into someone in front of me. So be responsible when you're driving out there. Anyways, don't crash like me. I also once rear-ended someone. I remember when I bought Madden because we were trying to read the package and the soundtrack, listen to the soundtrack, because that used to be a big deal with Madden. Anyway, sorry, I'm wasting time. So music plays at 1 to 2 volume levels. Each subject encounters a number of signs. Some require breaking. Reaction times recorded. So reaction times are response variable. We repeat the experiment at a different volume level. The order of those is randomly assigned for each subject. What kind of design? Right? We know it's not that. We know it's not that. And I want you to think about, why is this matched pairs? Which data values would we pair together? This isn't pairing the top 2 students. This isn't pairing one twin with another. It's not quite before and after, but it's similar. It wouldn't make sense for me to compare Chadima's reaction time at 1 volume to Sam's reaction time at another volume. Instead, I want to pair some values. I want Chadima's reaction time at 1 volume compared to Chadima's reaction time at the other volume to see if the volume was actually the factor, right? Instead of maybe their driving ability in general or other reaction time that's based on, whatever science. I want to compare Sam's 1 reaction time to Sam's other reaction time. So here we would want to pair the 2 reaction times that correspond to an individual person. That's another matched pairs. So that's it. Hopefully you feel a little bit better about matched pairs. I will see you all on Monday. Study this weekend. Send all your questions in Remind. Google Classroom, send me everything you can or want to so I can help you and you can help me. And have a great weekend.